In this video, I'm going to explain another key concept from translational motion, which is center of mass. So center of mass, as the name says, is a point on the object where the total mass of the object acts as if it is concentrated at this point. So you can imagine if you have a single object, this is my object over here, it's not symmetric, then this is a point where you can imagine the total mass of this entire object is concentrated. And if there is any force that is acting on the object, then that force will act at this point. So we know all objects, there's a force on all object, which is the weight force or the gravity force. And then the gravity force on this object will act exactly at this point over here. And that's why you can balance this object if you provide a support force at that point. So because of this reason, sometimes this center of mass is also called the center of gravity. If it's a symmetric object, then it's very easy to locate the center of mass because it will be right at the center of symmetry. But for an asymmetric object, it's slightly harder to figure out where the center of mass is. Okay. But in year 13 physics, what we are going to consider is not the center of mass of a single object, but we will have to look at the center of mass of a system, which is made of multiple objects. Let's consider a system made of two parts. So two objects. So we have a first object, which is mass m1, and then we have a second object, which is mass m2. Then the center of mass of the system is a point which will be on the line that connects these two masses. So it will be somewhere on this line. And it's a point where you can imagine the entire mass of the system is concentrated. So if I say that, let's say this is the location of the center of mass, this is also a point around which the entire system is balanced. So what does that mean? If I say the distance from the first mass to the location of the center of mass is x1, and let's say the distance from the center of mass to the second mass over here is x2, and then on each mass there will be a weight force acting on the object. So over here there will be a weight force acting on the mass m1, there will be also a weight force acting on the mass m2, and if I want to balance this entire thing, the weight forces will try to turn the entire system around the center of mass. So this weight force here will try to turn the system in the anti-clockwise direction, and this one will try to turn the system in the clockwise direction. So if I consider these two torques, so this is the torque for the first object, this is the torque coming from the second object, then these two torques will be equal to each other so that the entire system is in equilibrium. And if you remember from level 2 physics, torque depends on the force, which is the weight force over here, of the first object, and then multiply by the distance from the point around which we are measuring the torque. So that's our first torque, and then it has to be balanced by the second torque. So the weight force of the second object multiplied by the distance from the center of mass to the second object. And because these are weight forces, it will be m times g, acceleration due to gravity, and then the distances. So it turns out to be like this. And because you have the same g on both sides, this simply becomes, we can cancel out the acceleration due to gravity, and it looks like this. So in order to balance the system, the ratio of the two masses m1 and m2 is the same ratio as the two distances from the center of mass, but in reverse. That means if I have this mass over here, which is, let's say, slightly heavier, it's 3 kg, and you have another mass over here which is smaller and it's 1 kg, so the ratio of the two masses is 3 to 1, then what the center of mass will do is split the distance between the 2 points in the same ratio. The only difference is the lighter mass will be further away, so this side will be 3 parts of the distance, and this side will be 1 part of the distance. So that's how the center of mass will split the entire distance between the two masses. And if you know the distance, you can work out how far away the center of mass is from any of the object using this ratio method. So this is one way of working out the location of the center of mass, but there's a different way of doing the same, which is slightly simpler. It's based on the same logic, but that gives you a formula, and that formula will be in your formula sheet. So using this method, if I want to work out the location of the center of mass, I will have to choose a reference point. And this is the arbitrary reference point. So you can choose it wherever you want on this line connecting the two masses. So I'm going to choose it over here just to show you what I mean by the reference point. So this is my starting position, and I'm going to measure all the distances from here. So this is my first mass, and this is our second mass. And then I'm going to call the distance from this reference point to the first mass, that's our x1. The distance to the second mass over here from that same reference point, that is going to be x2. And then the distance from that reference point to the center of mass, this thing over here, that will give us the location of, or the position of the center of mass. So if you want to work out the position of the center of mass, then that position XCOM is equals to m1 x1 plus m2 x2 divided by m1 plus m2. So you can use this formula to work out the location of the center of mass as well. So you don't have to use the ratio method. This method is perfectly fine as well. And this is not limited to only two masses. If you have more masses on that same line, then you can keep adding the masses into this formula as well. So let's now look at an example where we apply this method to work out where the center of mass is. So the example we are going to consider is where we have two astronauts, and they are 1.1 meter apart. So I'm just drawing the astronauts as circles. Of course, it's not circles, but who cares? And the mass of this astronaut over here is 60 kg. The mass of this astronaut here is 50 kg, and they are 1.1 meters apart. So they are floating in space, and we have to work out where is the location of the center of mass of these two astronauts. Somewhere along this line that is connecting the center of mass of these two astronauts. And it will also be closer to the 60 kg mass, because the center of mass will be always closer to the heavier mass, because it splits the distance between the two objects in the ratio of their masses. So over here, the ratio of the two masses is 6:5. So the two masses m1 and m2, the ratio of the two masses is 6:5. So that means the distance over here will be split into the same ratio. So if I look at the distance x1 and x2, it will be just the opposite ratio, 5:6. That means this side over here, x1, this will be 5 parts of the entire distance, and this x2 over here will be 6 parts of this entire distance. So what you can do is, altogether there's 11 parts, and then if you want to work out the location of the center of mass from the 60 kg mass, so you're interested in this distance over here, then you can work out the location of the center of mass, which is 5 out of 11 parts of the entire distance, 1.1. So it will be 0.5 meters away from the 60 kg mass. So that's how you can use the ratio method to work it out. Alternatively, if you want to use this formula over here, then you have to choose a reference point. So to choose a reference point in questions like this, it's easiest if you choose the reference point at the position of one of the objects. So sometimes they specify that determine the location of the center of mass from M1. So in that case, you will choose the reference point over here at the center of mass of M1. And then we will measure all the distances from here. So then this will be our X center of mass, the location of the center of mass. This will be our X2, because that's our second mass, distance to the second mass, and our x1 will become 0 because we have chosen the location of the reference point at the center of mass of m1. So therefore x1 is 0. So now if I use that formula, x center of mass is equals to m1, which is 60, but then x1 is 0, plus m2, which is 50, and then x2 is the entire distance between the two objects, so it's 1.1 meters, and then divided by x1 plus x2. So if you do that, then you will get, so it's 55 divided by 110, and that gives us the exact same answer, 0.5 meters. So it does not matter which method you are using, whichever method you find easier to understand, use it, but both should give you the same answer. The key thing to remember is if we have a specific reference point, that means we want to measure the location of the center of mass from a specific object, then choose the reference point at the location of that object. Now, accidentally, if you have chosen the reference point on the other object, so if you have chosen the reference point over here, and then you measured the position of the center of mass from this object, so you have measured this distance instead, then there's nothing to worry about. What you can do is, if you have measured this distance, then you can subtract the total distance, this distance from the total distance to work out the location of the center of mass from the other object. So that is perfectly fine as well. The concept of center of mass is also very useful for collision or explosion problem. So if you have two objects and these two objects are, let's say, mass m1 over here, and then you have a mass m2 over here, m1, m2, and they are moving with their own velocity. So this is moving in this direction with velocity v1, and this is moving in this direction with velocity v2. So right at this instant, their center of mass will be somewhere on the line that connects these two, and usually it will be closer to the heavier mass, so not exactly at the center maybe. Now, because each of these masses are moving, the center of mass will move with the objects. So as the objects are moving in these two directions, so will be the center of mass. So the center of mass will kind of move in this direction with its own velocity. And if we call that v center of mass, which is the velocity of the center of mass, then we can work out what is the momentum of the center of mass. Now we know the center of mass is a point where we can imagine all of the mass of this entire system is concentrated. So this point, the center of mass, can be considered as a mass where the mass of the entire system is concentrated. So it's a point mass with the total mass of the system. Then the momentum of the center of mass, which is simply mass of the system times the velocity of the center of mass, this is equal to the total momentum of the entire system. So that's the relationship between the mass of the system, velocity of the center of mass, and the total momentum of the system. So it might look like the two masses are doing random stuff. They are arbitrarily moving, but they are actually connected to each other through the center of mass. So when they come and collide over here, so I should have drawn that properly. I think the direction of the center of mass will be more like in this direction over here. So when they come and collide, and then after the collision, if they move in two different direction, so if they move like that, so this mass m1 is now moving in this direction, and this mass m2 is now moving in this direction after the collision, then what will happen is the center of mass will also move, but it will keep moving in the same direction as it was before. So the velocity of the center of mass will not change. And why is that? If you look at this relationship over here, then the velocity of the center of mass is equals to the total momentum of the system, which we know is same before and after the collision if there is no external force, no net external force. Then this will not change, it will stay the same. and that divided by the mass of the system, which will also not change because we are still considering the same masses after the collision. So if both stays the same, then the velocity of the center of mass will also remain constant even after the collision. So what does that mean? It means that if there is no net external force, then the center of mass will keep moving in the same direction with the same velocity. That means V center of mass will not change after the collision. Here I have taken the same example as I have used earlier for conservation of momentum, because previously we have already worked out what is the total momentum of this system that we have over here. Because as you can see, before the collision, we have the 0.6 kg mass, which is moving at 1.8 meters per second to the right, the 0.5 kg mass, which is stationary. So if you add the momentum of these two objects, the total momentum turns out to be this over here, and it has to be to the right. So, and then after the collision, the total momentum will still be the same, because we have assumed that it's moving on the two objects are on a frictionless surface, so there is no net external force, and therefore the total momentum is conserved. Now, using that, we can work out the velocity of the center of mass. So that's what we want to do. We want to work out how fast the center of mass is moving and in which direction. Because the total momentum is to the right, then the center of mass of the system will be also moving to the right. So this will be the velocity, the direction of the velocity of center of mass before the collision, and it will remain the same. So center of mass will keep moving in the same direction with the same velocity even after the collision. So we can work out that velocity because we know that the total momentum of the system is associated with the momentum of the center of mass, which is equals to the mass of the entire system multiplied by the velocity of the center of mass. And then if we rearrange it, the velocity of the center of mass will be the total momentum of the system divided by the mass of the entire system. And because neither of these two are changing during the collision, the velocity of center of mass will also not change. So we can use the total momentum, which is 1.08, and the total mass of the system is 0.6 plus 0.5, which is 1.1 kg. And if we do the calculation, the velocity of the center of mass turns out to be 0.9818 meters per second. And because all the numbers that I've used, the least number of significant figures is 2, so I'm going to round it to 2 significant figures. So that's going to be 0.98 meters per second, and the direction is to the right. So before the collision, this is the velocity of the center of mass, and after the collision, even though the objects are moving in different direction, the center of mass will keep moving to the right at 0.98 meters per second. So this was the last thing that I wanted to explain about translational motion, and this is where we finish translational motion. So in the next video, I'll probably try to cover concepts from circular motion. So keep an eye on the channel. See you next time.